Okay, hey everyone. We're going to start here on the Lab 4 demo. We are going to learn some new tools for our Biostats toolbox. We are going to be learning about ANOVA and Kurzweil-Wallace today. So we're going to be using a new data set. It's going to be murder.sav, which sounds kind of scary to me, but it's in the same place as T Makes You Brainy and the cosmetic surgery data set. So go ahead and open that up. You can see here that I have it open in SPSS. This is a very simple data set. As you can see, we have street, which it looks like if we click on the three dots here, we have three different avenues in the data set here. And then murder is the actual number of murders that take place, and they're divided among which streets those murders take place. So hopefully we'll find here which streets not to live on so as to avoid all of the murders. But basically what we're going to be looking at in this lab is, as you can see, murder is a continuous variable, and then each of those three streets are categorical variables. So what happens when you have a continuous variable and then a variable that has more than just two levels? So if we remember back to lab 3, we did something very similar to this. But when we use a t-test, we do have a continuous variable, but we have a dichotomous variable. So the second variable in the comparison is, or in analysis is something with just two levels. So what happens here when we have three levels? And so the ANOVA and the Kurzweil-Wallace are actually very similar. They test slightly different things. But what we're going to do today is we're going to talk about the relationship between that continuous variable. Again, the number of murders that take place is going to be our count, or our continuous variable. And then we also are going to have a categorical variable, three or more groups. And so here we have three little guys here, and they're all holding hands, and they're showing here that the distribution of each of those different continuous variables actually looks pretty different. Okay, so ANOVA is used to find out when there is a statistically significant difference between the means of more than two independent groups. Okay, so we still have the word statistically significant difference here, so we are going to be going through that scary cloud of probability. We will have some type of a p-value at the end of this. So just as we did in our lab 3 demo, and then also in our lab 3 assignment, we're going to be working on actually interpreting our findings and figuring out whether we reject or fail to reject the null. So I have an example here that actually has nothing to do with the murder on different streets, but here we just have a sample research question. Is there a statistically significant difference in the average of BMI scores across low, medium, and high groups? So if that was my research question of interest, the next step is always going to be to create some type of a skeleton table. So based on my question of interest, I know that I have three different income categories. I have the low category, I have the medium category, and then of course the high category as well. And then what I'm going to look at here is the difference in mean BMI score. So BMI is going to be a continuous variable in this research question of interest. So I'm going to be looking at the mean and the standard deviation. Those are the two, the point estimate, the peanut butter and jelly that I would like to use here in this question. So I'm going to have hopefully a mean and a standard deviation for all of those people who are in the low income category, the medium, and then also the high. And then of course, because we're walking through that scary cloud of probability, we're also going to be looking for a p-value. Now, if you want to use the Kurzweil-Wallace test, and we're going to talk about the differences between these two and why you would choose one over the other a little bit lower down in the lab here. But basically here what we're doing with Kurzweil-Wallace is we want to find out if there is a statistically significant difference, okay? So we're still walking through that scary cloud of probability and looking for that p-value on the other side between the medians. So instead of the mean and the standard deviation, for Kurzweil-Wallace, what we're looking at is the median and the interquartile range of more than two independent groups. Okay, so the same question for our research question of interest applies here in this example, but instead of saying the mean BMI scores, the difference with Kurzweil-Wallace is we're looking at a median and of course the interquartile range. And so you see that reflected here in our skeleton table as well. We're looking for the median and the interquartile range of BMI in the low category, the medium income category, and then of course the high income category as well. And then hopefully, because we're taking that leap through the strange, scary cloud of probability, we're also going to get a p-value on the other end. And so we're going to go into both the ANOVA and then also the Kurzweil-Wallace using the murder data set. So go ahead and open that up in your SPSS data set, and we'll get going here. Okay, so let's dive into the ANOVA, which stands for the one-way analysis of variance in SPSS. So again, instead of thinking about BMI across income categories like we did above in our sample research question of interest, we're going to actually look at the data set provided by Andy Field right now. So step one, as always, is to build a table to answer our research question of interest. So with the two variables that we have in our SPSS data set, we want to understand whether there is a statistically significant difference in the average number of murders. Okay, so average, we're looking for a mean, not a median, which is why we're going to be using ANOVA, the average murder rates between the three different neighborhoods. And so if we were to take the table that we had above and just put in our variables of interest, here what we have is going to be the murder rate. And again, we're looking for the mean and the standard deviation for the three different neighborhood streets. And so instead of having the three different income categories, we've put neighborhood street here. And in the cloud of probability, once we walk through that, we're going to get an F statistic. We're going to have our degrees of freedom, which tells us a little bit about the variance in the data, and then also our p-value. Okay, so the F statistic and the degrees of freedom are your peanut butter and jelly, and then just as the mean and the standard deviation are your peanut butter and jelly. So that's how we want to set up our skeleton table. So the step two now, as we've added the statistical tests to our demos, is that we need to do a little assumptions testing, okay? So basically we use these assumptions to understand whether or not we should use ANOVA or Kurzweil-Wallace. Okay, now just a note here, it's very unlikely in the real world that you're going to see Kurzweil-Wallace used. Very bad for Mr. Kurzweil and Mr. Wallace. But ANOVA is a very strong test. It's a very robust test. So we're going to go through each of the assumptions, and we're going to see here in the data set that we may fail a few of the assumptions, but it would still be okay to go through and to use ANOVA because of how robust a test it is. So as opposed to the tests that we learn in Lab 3, you're very unlikely to have to use the non-parametric version of this test. ANOVA is really the one that you're going to see used in the literature, even if all of the assumptions are not met. So if we zoom down here, the first assumption is that the dependent variable is continuous. And that we can say very easily is a yes, okay? So we can look here in the SPSS data set, and we can see here that murder is a scale variable. It also doesn't have any values listed here, and it's actually the number of murders, which tells us that this is in fact a continuous variable. So then for that assumption, we get a nice big check. And now we have to ask whether the independent variable consists of two or more categorical groups. So again, we're just making sure that ANOVA is the correct test to use. And so we have to make sure that there are at least 3, if not more than 3, different streets that we will use in our analysis. And we know that that is true. We can check this by running a frequency table in SPSS. We can also do what we just did a few moments earlier and look to see that there are in fact 3 different streets included in the street variable in our data set. So that assumption also gets a nice big check. So we also have to make sure that the groups are independent from one another, meaning that the streets themselves are in fact different. And this is something that you inherently have to know about your data set, just as we know in the BRFIS data set that each of the individuals who are included here, are included in our states are individual participants. We don't have repeated measures. And that's the same thing here. We don't have, I guess, two of the three streets are not in fact the same street, that they are in fact independent from one another. So that assumption is also met, so we're good. So here what we would do is, for assumption number 4, is to make sure that there are no significant outliers. So if you remember back, goodness, I think it was Lab 2 demo, when we looked at the box plot for men versus women, and we looked at the depression scores, the BDI, we did see that there were some outliers. There were some men who had really, really high depression scores as compared to the average depression score in men. So what we saw there, what we saw on top of the category of the depression with just the males, we saw a bunch of little like asterisks at the top, which signify that there were in fact outliers. But here, if we go in and we just use our graphing abilities and we look at a box plot with each of the streets as our factors, and then the number of murders is over here on the y-axis, you can see that there are no outliers. We don't have anything outside the 95% intervals that we have here. So there are no outliers. So we can say that assumption 4 is met. So now what we need to do is we need to check and make sure that the dependent, or the continuous variable, murder in this case, is actually normally distributed in each group. Okay, so we do this very similar to what we did for the t-test. We wanted to look and see if each of the different categories were normally distributed. We have to do the same thing here. Are the number of murders on each street normally distributed? So in order to do this, we're going to go to SPSS, and we're actually going to check this. So we're going to go here. Why don't we go over here? And we're going to go to Analyze, Descriptives, and then down here to Explore. We want to bring in Street as the factor, and then our dependent variable is murder. When we go over here to Plots, we want to do a histogram plot, not a stem and leaf plot. And we also want to figure out whether or not these are normally distributed. So we can go ahead and check this normality plots with tests. Okay, so we are going to get some p-values from this test. Go ahead and say continue, and then we can go ahead and say okay, sort of, and then my output is behaving a little bit strangely today. Okay, so here what we can see is we can see that there are, we have each of the 3 streets here, okay, and then here we can see on each of the streets the mean. Okay, where is the mean here? There's the mean right here. This is the mean, and then the standard deviation, and then we can see the mean here on Acacia, and then also down here in Rue. And then if we go down here and we test, here is our test of normality. So we're going to come back to that in just a second. But we're going to see here that we have the frequency of each of the different murders for Ruskin. So this looks pretty normally distributed, right? We have sort of the most number of murders are here sort of in this area. And then this one, maybe not. This is sort of slanting downward, but I don't know, maybe. This one definitely does not look normal to me at all. We have several different peaks. It just seems a little bit strange. Now, the other thing to notice here is that we only have 12 observations per street. So here you can see the number here is 12. So we have pretty small sample sizes. So we might not get any normally distributed data, or it might not look as pretty as we'd like it to. But if we go back up here, and I actually think that I've screenshotted this for us here. Yeah. So what we have here is we have a significance number here. So again, we have smaller samples, so we only have 12 different observations per street, your BRFIS samples are going to be much larger. So you shouldn't fail this assumption with BRFIS. But for example, in your capstone projects, you might fail this assumption because sometimes for capstone, we run into small sample size issues, but it really shouldn't be that big of a deal. But basically you have two different tests of normality. Here we would use this one for very large samples. We would use these statistics here for smaller samples. So because we have smaller samples, we're going to use this Shapiro-Wilk test. And what we want to look for here is we want to look for anything that is statistically significant. So anything that is below 0.05 is going to say that you are in fact normally distributed. So it looks like here that Ruskin, and if we go back here, Ruskin was the one that there it is. This is the one that we thought looked a little bit more normal, right, than the other ones. And so in fact, we find out that when we go to the test for normality, in fact, it does stand the statistical test. That does come back as normally distributed, whereas the other two do not. So we have 0.64 for Acacia, and then we have 1.44 for Rue. So both of those technically fail. And again, if we go back to the pictures here, this was like a maybe, and it just fails the statistically significance, the alpha level of 0.05 because it's 0.06. This one really fails. This is definitely above 0.05. So just looking at the data, and how it's distributed, it looks pretty good, right? I mean, it matches what we were assuming if we go here and we look at these statistically significant numbers in the test for normality. So I would say here that this assumption is mostly met. I mean, 2 out of 3 of the groups were mostly normal. One definitely was. One was really, really close. The other one wasn't. But I would say, again, because ANOVA is actually a very robust test, that I would not throw away ANOVA for this data set quite yet. It hasn't sort of crossed over the threshold that ANOVA wouldn't be able to handle. Okay, so now the 6th assumption, and I know that there are a lot of assumptions, but ANOVA is a pretty intricate test here. But we have to test for the homogeneity of variance. Okay, understanding exactly what that means and the ins and out of that is more of a graduate level issue. I just want you guys to know that there is an assumption of homogeneity of variance, and that just means that the noise around the distribution of each of the murders on the street should be about the same. Again, if that doesn't make sense, you can just sort of put it in the back of your head and just make sure when you take a graduate level biostatistics class that you tell them that Dr. George did tell you that there was this assumption for ANOVA. But what we're going to do now is we're going to go and we're actually going to test this. So if we go to, if we go here, we go to Analyze, and we go down to Compare Means. Okay, and then so this is where our independent samples t-test was. We're doing the same thing, we just have more levels now. So we're going to go down to the one-way ANOVA. Our street is still our factor list, and our number of murders is still our dependent list. And if we go here to options, the homogeneity of variance test is right there. So we can go ahead and say continue and say okay. And I think I've screenshotted the outcome here, so we can just sort of go back here. And I did. So the test for homogeneity of variance is right here. So here what we can look at is we can look at this statistically significant number here. Now we know that even though SPSS says that the p-value is 0.000, we know that that's not actually the case. But here, when you have a very small p-value, it means that you're violating that assumption. So we actually, sometimes we want statistically significant p-values and sometimes we don't. And this is a great example of when we do not want to see a statistically significant number here, but we did. So unfortunately, we fail this assumption. So this assumption is not met. So those are all of the assumptions that have to do with ANOVA. And you can see here as we get down to assumption 6, we're definitely failing this assumption, but I'm going to go ahead and say, you know what, let's just try to do ANOVA. First of all, I want you guys to learn how to do it, so we're going to do it anyways. But just know that even if this was in the real world, you could say that even though Assumption 6 was in fact violated, that because ANOVA is a robust test, you're going to go ahead and use it anyways. Okay, so in fact, we have decided to use ANOVA even though our last assumption was violated. We've actually done all of the tests in SPSS that we need to do in order to fill in our skeleton table. But just to reiterate, what you want to do is you want to go to Analyze, Compare Means, and then One-Way ANOVA. Your street is your factor list, and then your number of murders is in your dependent list. And in fact, one of the outputs that was generated from doing that test was in fact the ANOVA results. So even if we go back here just to our output, you can see that this was our test of homogeneity of variances, which helped us decide whether or not we could move on with Assumption 5. And then here is actually our output for our ANOVA. Okay, and please remember what we've also done. If we got zoom up here, here you can see the box plot, making sure that there were no outliers. That is an automatic something that comes out, a result that comes out with ANOVA. But if we go all the way back up to our Explore, all the way back up to our Explore command, which was way up here, we could grab our mean and our standard deviation for each of the different streets, right? Those are statistics that we want to pull into our skeleton table. So if we come back here to our Lab 4 demo, we have our ANOVA, and then if we go back up to the information in the Explore command, we can fill in that the mean and the standard deviation for Ruskin, for Acacia, and then for Rue. Again, that's through the Explore command. And then our F statistic, our degrees of freedom, and then our p-value are right here. So what we want to pull in here is our F statistic, which is right here. Our degrees of freedom, you can actually give both of these. So you do a 2 to a 33 and you have a comma between the two. And then also our p-value is equal to 0.005. So again, what we're doing here is we're looking to see is there a statistically significant difference between the average number of murders on each of these three streets? Now, let's just say we didn't have this p-value. We were just looking and we were just going to take our opinions. So this is less than 1 murder. This is a little bit over 1, and this is almost 3 murders. So if I were looking at the property value on these 3 streets, I would definitely prefer to live at Ruskin than I would at Rue Morgan. So if I were to just sort of look at this and not know that there was a statistically significant p-value, I would say that those 3 numbers are in fact different. Definitely Ruskin and Rue are different. Acacia is right in the middle, so I'm not quite sure whether these 2 averages are different or these 2 averages are different, but what this output is telling me is, in fact, there is a difference. It is not telling me where that difference exists. And this is something that students always miss on their Lab 4. If you find that your ANOVA output is statistically significant, you are not done. Just telling me that, yes, there is a difference in the means of murder on each of these 3 streets is not enough. I want to know more than that. I want to know which streets are the ones that are different from one another. And so that's when we have to go in and do our post hoc tests. Okay, so for our post hoc tests, we can actually just run this all at the same time. So regardless of whether we get a statistically significant result in our ANOVA, we can run a post hoc test just in case. So basically the ANOVA is telling us that there is a difference, but the post hoc test is telling us where that difference exists. So let's go ahead back into our SPSS data set. So we're going to go to Analyze. We're going to go to Compare Means. Oops. We're going to go to One-Way ANOVA, and then we're going to go ahead to the Post Hoc tab, and we're going to check Tukey. Now, I have to admit, I have really no idea. I mean, I've seen Bonferroni before. I've definitely used Tukey before, but some of these other ones, I'm really not quite sure what they mean or what they are. Waller Duncan, I guess I've used that as well, but you don't have to know what all of these different names are. These are basically the last names of people that have developed the statistical test. Honestly, you don't have to know any of them besides Tukey, because that's the one that we're going to use in this class. So all you need to do is check that box and go ahead and say continue. Now this is the exact same one-way ANOVA that we ran before, so just go ahead and say okay. My output's being weird today. Okay, and so now what we have is the same. This is the same as we had before. The test for a homogeneity of variance. This is our exact same ANOVA output. But then now what we have here, if we scroll down a little bit, is this post hoc test, this multiple comparisons. So this is a lot of numbers to look at. And so if we go back here to our demo, I've screenshotted this for you. So basically what this is looking at is it's looking at Ruskin, and it's asking, is Ruskin different than Acacia? And if you follow this through, you can see no. This is not statistically significant. This is above 0.05, which is telling us that Ruskin and Acacia, and it actually does this again for us because it does Acacia versus Ruskin because they don't know whether or not order matters. It does not here, but sometimes it will, is a p-value of 0.783. Which means it's not statistically significant. But if we look at Ruskin to Roux, we can see that we do have a statistically significant difference. That's a p-value of 0.006, which is telling us that the mean of less than 1 murder versus almost 3 is in fact statistically significantly different. And then the way that you want to think about this, for me, it just makes sense to actually write them. So this is Ruskin, and I'm reminding myself of what the mean and the standard deviation was, versus Acacia. This is telling me that's not statistically significantly different. However, Ruskin and Roux, 0.83 versus 2.92 is statistically significantly different with a p-value of 0.006. And if we just look at Acacia and Roux, so the third combination here, a mean of 1.25 versus a mean of 2.92, we see that this is also statistically significant. So we see that this is 0.030, which is less than 0.05, our normal alpha level. So we can go ahead and not just say that there is a difference between all of the streets, but we can go a step further and say it's actually Ruskin and Roux and Acacia and Roux, but there is no difference between Ruskin and Acacia. Okay, and this becomes a little difficult to synthesize the results. So what I've done here is I've actually given you an example of how I would do this. So there was a statistically significant association between the average number of murders and the neighborhood location. So that was our original question of interest. But just telling me that there was a difference and then not telling me where that difference existed is not what we're going to do here. So then what I want to do is after we do the Tukey post hoc test, we can see the average number of murders on Ruskin is different than Roux, and Roux is different than Acacia. However, there was no statistically significant difference between Acacia and Ruskin avenues. Okay, so let's go ahead and look at the non-parametric version of ANOVA, which is the Kurzweil-Wallace. So again, ANOVA is a very robust test. However, if we believe that we have failed our assumptions so dramatically that there is no recovery, we have to go ahead and use the Kurzweil-Wallace. I'm going to show you how to do that. But instead of reporting the mean and the standard deviation from our Explore test that we ran before, we want to make sure that you're reporting the median and the interquartile range. So again, our research question of interest changes slightly. So is there a statistically significant difference in the median number of murders between the neighborhoods? And so here we have the median and the interquartile range, but really everything else is pretty similar. Save this, our new test statistic is an H statistic, and the degrees of freedom and the p-value. Okay, so in order to use the Kurzweil-Wallace, it's a little bit of like a click, 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 click that we have to go through here. So let's just go ahead. I have it all screenshotted here, but let's go ahead, whoops, and reset this. And let's go up to Analyze, and we go to the non-parametric tests. We want to choose independent samples. So something kind of weird comes up. This looks like a mistake. It looks very different than the other windows that usually pop up. Non-parametric tests are a little bit strange, if I'm going to be honest with you. But what we want to do here is we want to compare the medians across different groups. So that's in our objective. That's what Kurzweil-Wallace is designed to do. That's what our research question of interest is asking. We go to fields. This automatically populates for me. It knows that this is our dependent variable, our scale variable, and this is our group variable. Honestly, it's probably because we only have 2 variables in our whole data set here. If you had more factor lists and possible dependent variables, you may have to pull it from what would be a big list over here in your Bergfus data set. But it automatically populates here. We're going to go ahead and choose our test, and our test is going to be Kurzweil-Wallace, one-way ANOVA, and it automatically says to compare pairwise samples, which is all great. And so we're going to go ahead and say run. Okay, so a lot of different things are coming out here. We have a lot of different tests that are being run at the same time. So what I did is I went ahead and I screenshotted those that are important for you to pay attention to, and indicated where you should be getting the information that you need in order to decide whether or not you're going to reject or fail to reject the null hypothesis with this test. So here, just again, showing you what it is you need to do for the different windows. This is so lovely. I wish this did this for all SPSS output, but it tells you whether you reject. This says retain the null hypothesis. I don't love it, but this one is telling you that we should reject the null hypothesis, and it's showing us here with a significant statistic here. So the 0.046 is less than 0.050, so we're going to go ahead and reject the null hypothesis. And again, it's telling you what the significance level is, or the alpha level here. What this is telling us here, the pairwise, so it's comparing all 3 of the streets here. Okay, so this is the Acacia Street, this is the Ruskin Street, and this is Rue Morgan. This is sort of a visual representation of the comparisons between them. So you don't actually have to go in and do a post hoc test. Kurzweil-Wallace will automatically do that for you. This is showing you that what the overall median is 1, and so it has a nice line that's running through for you here. And then these are the actual numbers that you need to get for your skeleton table. So we have your H statistic, your degrees of freedom, and then your 2-sided p-value. So again, these are your post hoc results. So it's telling you, in my honest opinion, a little bit more plainly, which of the 2 streets are actually different. And so there's a little bit of a difference here in terms of the only street that's statistically significantly different from each other is the Ruskin and the Rue. We no longer have a statistically significant result. If we look at the adjusted p-value here for Acacia and Rue, which was the case in the ANOVA, so we have slightly different results here with the Kurzweil-Wallace. So if we zoom down here to our table 2, this is how we would fill it in. We have the murder median and interquartile range for each of the 3 groups. Again, we did that with the descriptive statistics and the explore command that we did first. So we're pulling those directly from that output. And then here we have the H and the degrees, the H statistic and the degrees of freedom, along with the overall p-value. And again, we don't have to run any post hoc tests, but we do want to talk about what our post hoc tests are when we synthesize the results. So there was a statistically significant association between the median, right? Not the mean, but the median number of murders and each of the neighborhood streets or locations. And then here are the statistics from that output table. And then the comparisons, the pairwise comparisons showed that it was only Ruskin and Rue that were statistically significant from each other. There were no other statistically significant differences between Acacia and Ruskin and Acacia and Rue when we use the Kurzweil-Wallace test. So that is the end of our Lab 4 demo. Again, we are adding our two tools to our biostats toolbox, both ANOVA, which is the parametric version of the test, and then also Kurzweil-Wallace, which is the non-parametric version of the test. And again, the reason that we needed to add this tool to our biostats toolbox was because we were dealing with variables that didn't fit into any of the tests that we previously knew. We had murder, which was a continuous variable, and then we had street. And we didn't just have two different streets that we were comparing, we had 3 streets. And so we weren't able to use the t-test. We had to expand our biostats toolbox to actually use ANOVA. ANOVA is one of those tests that you actually see quite a bit in the literature. So we thought it was important for us to add this here into your biostats toolbox. And hopefully this made sense. We will review these in class, but I always like to give you guys my recording so that you can listen to it at your own time and at your own pace. So good luck with Lab 4. We will introduce that shortly.